You know what I miss? Graphing.
Me too. Except, I can't see how it applies here. It says we're going to be solving single variable equations. That's like only having an x. If we graph something that only has an x, that's like graphing a whole series of vertical lines. I don't see how that's going to make any sense.
You will, don't worry. We're going to look at how to solve an equation like this using graphing. And yes, there is no y involved, it's just an x over here, x over there. And there are algebraic ways to solve this, where we could do things like make things go to different sides, maybe distribute, open up some brackets, all that jazz. But it is also possible to solve something like this by graphing. And that's going to be useful down the road when you have perhaps more complex equations to solve by graphing. Ones that won't cater as well to algebraic processes. So our process here is to split this up into its left side and its right side. And essentially we're going to graph y equals this left side, we'll graph y equals this right side, and we will find their point of intersection. Now when we solved systems, the point of intersection was the solution. But that involves an x and a y, and this equation only involves x's. So our solution will only be the x value of that point.
All right, let's take a look at what you mean by all of that. So as Mr. A said, we are going to introduce two equations by letting y equal our left-hand side. So our left-hand side here is 1/2 x minus 2, all in brackets, minus 3. And the second equation where y is equal to our right-hand side. So negative 5/6 x plus 4. Now we are going to graph each of these. As we graph them, it's super important that we make sure that we label our axes and we make sure that we indicate some sort of scale. So here I'm going to have x, here I'm going to have y, I have 1, and 1 is my scale there. Now, when I'm taking a look at the first equation that I need to graph, it's not really in a form that I can graph really easily. My instinct is, when possible, to go straight into slope-intercept form, but I can see that this is actually going to be way easier to convert to slope-point form. So I'm going to convert 1 to slope point. You don't have to write this down here, but just so that you can kind of grasp what I'm saying. So I have this equation. To get it to slope point form, all I have to do is kick that negative 3 to the other side. So y plus 3 is equal to 1/2 x minus 2. So now that I'm in slope point form, I can see that I can start by graphing the point 2, negative 3. So 2, negative 3 is down here. And then my slope is positive 1/2. So rise 1, run 2. And I like to continue until I run out of space here. I'm going to connect the dots with a straight line. Make sure that as I do so, I'm hitting all of the points. I'm going to draw arrows on either side. And I'm going to label that line as appropriate, right? This is equation 1, so I'm going to label it with a 1, so we know which one's which. Now, if I want to graph line 2, well, that's already in slope-intercept form. So I see my y-intercept is 4, my slope is negative 5/6, so I go down 5/6, which is this point here. I can't backtrack, but to be honest, these are the only 2 points I care about because I've already found my point of intersection. Woo! But I do have to finish things off. I have to draw the arrows on the end. I should label what that line represents. Now, my point of intersection is x, y is equal to, what do we have here? 1, 2, 3, 4, 5, 6, negative 1. Now, as Mr. A said, this is not our solution. We shouldn't be saying, well, this is our solution to our equation, because that's saying my x value is 6 and my y value is negative 1. And the original equation had no y values. So it wouldn't make sense to indicate it like that. So my final solution would simply be x is equal to 6.
Ta-da! There are a couple more examples. There's this one, and then there's one after it. Try them yourself. So give them a go. See if you can follow those steps. Graph the left side, graph the right side, and find that point of intersection and work with it. But do pause this video. And welcome back. I'm going to graph this thing. I'm going to start by graphing y equals x minus 1. And then I'll be graphing y equals negative 2x plus 5. That's my left side and my right side broken up there. Of course, I'm going to label my axes. I'll label my scale in a moment or 3 afterwards. Let's figure out where these lines are going to cross. Y equals x minus 1 goes there. Whoa, hold up.
Whoa! Who invited you?
I saw the negative and I just went to town with it. Anyways, it's got a positive slope. I figured that out eventually. And we're good. I play my connected dots. That's in there. Other one is negative 2x plus 5. And that's at 3, 4, 5's up here. Negative 2, it's there. And that's my collection of points. Now to do this properly, I do make sure that I indicate which line is which. This is the line from equation 1. That's the line from equation 2. And their point of intersection, we'd be able to tell if this thing had a scale. So I should probably indicate that somewhere. Let's call that 4. Let's call this 1. I'd indicate it here, it just seems crowded and cramped, so I didn't. We've got a point of intersection at, at 2, 1. Therefore, my solution to this is x equals that x value of 2. Whoa, who put green here? Boom.
All right, last one. If you didn't pause the video for this example, pause it now. Oh, and unpause it so that you can listen to the rest of it. All right, we are starting off by breaking things up. So y is equal to my left-hand side, my 1/3 x minus 4, and my equation 2, we're going to break it up. Y is equal to my right-hand side, so 3/5 x. Now, taking a look at equation 1, this is actually already in slope point form, except on my left-hand side, really, what I don't see but really exists is that -0, right? So the point that we would start by graphing is 4, 0. Now, I would start graphing it already, but I don't have my axes labeled. I don't have any of that stuff down. I don't even have a scale indicated. So I have x and I have y as my axes. I'm going to label this as 1. I'm going to label this as 1. Oh, so cute. And I am going to plot my first point. So again, from equation 1, it's in slope point form. We have the point 4, 0. So that looks like 1, 2, 3, 4. And my slope is 1/3. So up 1, rise 3. And going backwards, down 1. I said up 1, rise 3. I meant up 1, run 3. There we go. Now I understand what words sound like. Of course, make sure my line's straight, and it actually goes through the points, not just close. I draw some arrows over yonder, and I label it like a champ. And now I graph equation 2. So I have y is equal to 3/5 x, which means my slope-intercept form, I would have an intercept, a y-intercept of 0. And I have a slope of 3/5. So I would go up 3 over 5. I would also go down 3 and backwards 5. And I can draw a line that connects those, slap some arrows on for good measure, and label it. And I can see that my point of intersection, when I solve here graphically, would be xy is equal to, what do we have? -5, -3. But again, we're not looking for the point of intersection as a final answer. We want our solution to only include our x value. So we have x is equal to -5 as our solution.
One final note is that it's possible to verify your solutions, and you can verify them algebraically. Same as we verified things when we dealt with systems. That's to break things up into a left side and a right side and see what happens when you plug in your solution. So where this left side says something like 1/3 of x minus 4, and this right side says 3/5 of x, what happens when x is -5? So you can plug that kind of value in here, see what happens, and make sure that your left and right sides equal the same thing. And if they do, everything's all hunky-dory, and you're good to go. And if they don't, well, then there must have been a mistake somewhere. That's just worth noting.
All right, that's it. That's all. We will see you in the next lesson.
There is some practice work. Don't forget to do it. It's pretty great.
Adios, amigos.
Bye.